Section 9.2, Direction Fields and Euler's Method. In general, suppose we have a first-order differential equation of the form y prime equals f of xy, where f of xy is some expression in x and y. If we draw short line segments with slope f of xy at several points, the result is called a direction field or slope field. Let's do an example where we sketch the direction field for the differential equation y prime equals x squared plus y squared minus 1. So we need to make a little bit of a table. So how about we have x, y, and y prime. When x is, how about we look at a bunch of y values at 0. We can look along the x-axis first. So when y is 0, and let's look at, how about x is minus 2, and then we'll go all the way to positive 2. So minus 2 for x, we plug that in. And we plug in 0 for y. So we end up with 4 plus 0 minus 1. So y prime becomes 3. So that means that we should draw some axes. A little lower. And I'll go farther back a little bit. We've got going up to, here's 1, here's 2, minus 1, and minus 2. Maybe I'll make this a little bit farther. Okay, so we just did minus 2, 0. So that means that there's a little line segment at minus 2 that has a slope of 3. So instead of drawing an entire line with a slope of 3, which would look like, I don't know, something like that, I'm just going to draw a tiny little line segment with a slope of 3. And then I do my next point. I'll go to, still along the x-axis, so I'll still go along y equals 0. I'll go to minus 1 now. Well, plugging in minus 1, I squared that, plus 0, minus 1, so the slope is 0 over there. So I should make a nice segment over here with slope 0 at minus 1. It's a nice horizontal little line segment. And then at 0, I can see that I'm going to go for 0 for y also, because I'm just choosing any 2 points for these guys. This is your choice, but then this is the result. So this is actually 0 plus 0 minus 1, which is minus 1. So that means I should draw a little line segment that's going down with a slope of minus 1 at 0. And then my next point, I'm going to still go along the x-axis. I'll go to 1 now. So at 1 comma 0, if I plug in 1 plus 0 minus 1, I get a slope of 0 again. So another horizontal line segment at 1. And then at 2, we should get, if we plug in 2 and 0, we get 2 plus 1 is 3. Sorry, 2 squared is 4 minus 1 is 3. So I should get another line segment of 3 over there. And you keep doing this. So we get, if we want the next row, we could do minus 2, 1 this time instead of minus 2, 0. You plug that in, you get 4 for the derivative, so the slope is 4. So minus 2, 1, I should make this, let's see if I can make this even steeper. Actually, let me go higher. So if this is 1, so I'll make this over there. And that's pretty steep, because it's a slope of 4 now. And let's say there's 2. So you can keep going like this and fill in the rest of the table and the rest of the slope field. You don't have to, limit yourself to the table. Once you get used to it, you can just start making all of these slopes in your head. You can compute all of the derivatives in your head without having to actually write down the table. But it's, I think, nice to see it all in action. So you should end up with something roughly like that. Notice that after I finished with, integer points from -2, -1, 0, 1, 2. I went halfway in between also, just to have a more complete graph. And you can see why I only went up to 2, because this is very labor intensive to make one of these things by hand. Let's do the second part of this problem now. We'll use part A to sketch the solution curve that passes through the origin. So, as you've seen before, for a differential equation, there are lots of little potential solution curves. You could start almost anywhere you want and then go through. It all depends on your initial value, usually. So, we want the one that passes through the origin. So, let's look at the origin, and let's follow along the path. So we do that, and we roughly get a solution curve like that. So I think that we can draw that now. It looks like our solution curve should be this polynomial-like looking thing. Or it could even be a trig function. Suppose that in the simple circuit of the figure, the resistance is 12 ohms, the inductance is 4 henries, and a battery gives a constant voltage of 60 volts. Let's draw a direction field for L times di dt plus Ri equals E of t with these values. So that means that L is 4 because our inductance is 4 henries. We have that our resistance is 12 ohms, so R equals 12. And we have that our voltage is a constant 60 volts, so E of t is a constant 60. So if we plug that in, we get 4 times di dt plus 12i equals 60. In this case, I is our y, and di dt is our y prime. So di dt is equal to 15 minus 3i. So if we draw a slope field, it should look roughly like this. Very roughly. That's not t though, it's not x, it's t. And this is not y, it's I. So if we look at 15 minus 3i, you can see right off the bat that by inspection, if I is equal to 5, then the slope is just 0 all the way through. So how about I start with that? I'll go 0, I'll go 1, 2, and 3, and I'll go 2, 4, and 6, how about? So constant 5, sorry, at I equals 5, it's a constant 0 for the slope, because plugging in 5 gives di dt equals 0, so I'll just draw a whole bunch of little line segments with slope 0. And then if I go a little bit higher, let's say I went to 6, 15 minus 3 times 6 is negative, because 15 minus 18 is negative 3, so this is a slope that's going down 3, and it doesn't matter what the value of t is, because E of t was constant 60, so no matter where I go, this thing will be constant slope of negative 3. So I'll just draw all of those little slopes. If I look at, let's say, 4, 15 minus 3 times 4 is 15 minus 12 is positive 3. So I can just draw the reverse. And then I can fill in the rest of the slope field similarly by just looking at different I values, because it doesn't matter what t value is, all of those slopes along that same I value are going to be parallel. So you should end up roughly with a slope field that looks like that. Let's see what we could say about the limiting value of the current. It looks like any slope field we draw, so we drew like one like this, or one like this, or one like that, they would all end up stuck over here, not going past 5. Similarly, if we drew slope fields coming out over here, they would still not go past 5. They all just kind of end up corralled at this limiting value of 5. So it looks like all the solution curves approach 5 amps. So we could say the limit as t goes to infinity of any solution curve I of t should equal 5. Let's identify any equilibrium solutions. Equilibrium solutions are solutions that make our rate of change stop. Once the rate of change is 0, then nothing's happening anymore and everything's at equilibrium. So let's see what makes our solution, our di dt equals 0. Well, that was how we started drawing this thing in the first place. We noticed that plugging in 5 makes this thing 0. If you look at the solution curve that goes over here, that solution curve cuts through every single 0 slope line segment. So that's an equilibrium solution. So we can say that when I of t is 5, that implies that di dt would be equal to 15 minus 3 times 5, which is 0. So that's an equilibrium solution. Equilibrium solutions don't have to just be straight lines, though. In general, let's say you had a differential equation that actually had some of your independent variable involved. In this case, there's no t, there's just I and di dt. But let's say you had something like y prime equals x squared minus y. Then in that case, you would expect an equilibrium solution for y to be x squared, because plugging in x squared would give you 0. X squared minus x squared would just cancel. So in that case, you would expect that your slope field would have a whole bunch of 0 slope line segments in the shape of a parabola, if you were to draw them. For that particular solution curve. But I digress. Our example just happened to be that our equilibrium solution was a nice straight line. If the switch is closed when t equals 0, so the current starts with I of 0 equals 0, let's use the direction field to sketch the solution curve. So we go back over here. I want to try to sketch the solution curve starting at 0. So we're starting at the origin. Looks like if we follow the flow, then it looks something like this for our solution curve. So we can bring that down over here. It looks like if here's I and here's t, then here's our solution curve when I of 0 equals, starting with the initial value of I of 0 equals 0. You could have tons of different solution curves, remember. It could have started anywhere, but we were just told start at 0. In our case, this differential equation is called autonomous because the independent variable is missing from this right side. As I said before, that's what made our equilibrium solution a nice flat line. So when we have autonomous differential equations, that means that the slope at every single point corresponds to points with the exact same, when the y-coordinate at every single point is equal, then the slopes of all those points correspond for all those little line segments. That's how we drew our slope field to begin with. For every single one of these y values, all of our slopes are the same for any t value, which is what happens when you have an autonomous differential equation. So what this means is that if we have one solution to a differential equation, then we have infinite more solutions just by shifting our solution over. We can just maybe draw it a little better. So I could maybe shift over to 1. Like that. And then I've got a solution by shifting my pink line over to 1. And then I could shift it over to 2. And I have another solution to my differential equation. Euler's method says that approximate values for the solution of the initial value problem y prime equals f of x y, where y of x naught equals y naught, with step size h, at x values xn equals our previous x value xn minus 1 plus h, are yn, so our y value is equal to yn minus 1, our previous y value, plus our step size h times the value of the function at the previous y value. So this is very similar to Euler's method as we did before, except that now what we're doing is we look at the solution curve to a differential equation. So let's say here's our solution curve. I can do it pink if you want it to be similar to what we did before. So we have a particular solution curve. We want to try to approximate that solution. So what we do is we approximate it using linearizations. So we draw some line to approximate it. But then notice if I keep drawing the line, it becomes a very poor approximation the farther I go. So what we do is we stop and we adjust and we draw another line. But then again, we get the same issue. If I keep doing that, it gets to be a bad approximation, so we adjust. And we change it to another line. And we keep doing that, drawing more and more line segments for different linearizations, and we can keep approximating different y values this way for our solution. So we don't actually get an equation for the solution. What we do is we get a table of values that should hopefully match the table of values, or at least closely match the table of values of the actual solution. And if we want it to match closer and closer, obviously we make our step size h smaller, because the closer we get, the sooner that we pivot and draw another line segment, the more line segments we draw, the better our approximation becomes. Notice that this looks a little bit scary and looks a little bit like a mess, but it really is just a linearization. Remember that for point slope form, we have y minus y1 equals our slope m times x minus x1, which was our linearization essentially. Also remember that our slope is our derivative. F of xy is our derivative. That's what differential equations are, so that's where this m comes in. That's f is m. Our change in x is our step size h. And our y1 is just on the other side. You could just move it over. So let's use this linearization to come up with a table of values to approximate the solution for the initial value problem y prime equals x plus y, where our initial value y of 0 is equal to 1. So how about we do a step size of 0.1? That should be pretty accurate. Accurate enough. And our starting x value is 0. And our starting y value is 1. Then our function, or our derivative, which is slope of the tangent line, is x plus y. So let's get, well, we started with 1 point over here. We know that 0, 1 is definitely on our solution. So let's get our next point. So we'll get y1 now. That's equal to the previous y value plus our step size h times f of our previous point, x naught, y naught. So our first y value is 1. Our step size was 0.1. First x value is 0 and y value was 1, so we get 1.1 for our y1, our second y value. Let's get y2 now. So y2 will be y1, our previous y value, plus our step size times f of our previous point, x1, y1. So now notice we're plugging in y1, so we plug in what we just solved for, which was 1.1. and we use our step size of 0.1 again. But notice now we need x1, y1 in the start of our function where we add them together. So if our first point was at 0, so that would be 0 over here, and then we move over h, that means that our second x value is 0.1 more than 0. So our second x value is just 0.1. And we already know our second y value is 1.1, so that ends up being 1.22 for y2. For y3, we do the same process again. y2 plus h times f of our previous point, x2, y2. We get 1.22 because that's what y2 was, plus our step size 0.1 times our next x value. If the first x value was 0, then it moved up by 0.1. The next one will move up another 0.1 because that's what h is doing. And our next value for x would be 0.2. We add that to a y value because that's what our differential equation is telling us to do, and we get 1.362 for y3. So what this is saying is that for our solution curve, y of 0 is absolutely equal to 1. Y of the next point, y of 0.1, is approximately equal to 1.1 on our purple line, using the blue one. Then y of our next x value, so y of 0.2 is approximately 1.22. Y of 0.3 is approximately 1.362. So if we keep, doing this process over and over, we can get a nice table of values. So how about I draw that? So you should end up with a table of values that looks something like that. And remember what this means. This means that these values approximate the table of values we'd get if we were actually looking at the solution curve itself instead of just approximating it. So we would expect that on the solution curve, for example, the actual y value at 0.8 would be approximately 2.487178. In example 2, we discussed a simple electric circuit with resistance 12 ohms, inductance 4 henries, and a battery with voltage 60 volts. If the switch is closed when t equals 0, we model the current I at time t by the initial value problem. di dt equals 15 minus 3I, where I of 0 equals 0. Let's estimate the current in the circuit half a second after the switch is closed. So we're estimating values in our solution curve that we drew in purple. So pink or whatever color it is, I don't even know. So h, let's choose to be 0.1 again for our step size. We'll start at time 0, and we'll start at I of 0, which is 0, and we will look at f of ti, which is our differential equation, or the right side of our differential equation. So let's use Euler's method. Let's look at our next I value, I of 1. That's going to be our previous one, 0, plus our step size 0.1 times 15 minus 3 times our I value of 0, because that's what our previous I value was. So that's 1.5. And next for I2, we get that it's our previous one, 1.5, plus our step size 0.1 times 15 minus 3 times 1.5, which is 2.55. And we keep doing this. We get I of 3, which is 2.55 plus 0.1 times 15 minus 3 times 2.55. So 3.285. I of 4 is 3.285 plus 0.1 times 15 minus 3 times 3, I think it's 3.285. Yeah, I was about to plug in 2.55 again. and we get 3.7995. And then I of 5 can be our last one because it said we only needed to go half a second. So we were doing a step size of 0.1, which is a tenth of a second. So 0.5 will be all we need. Thank goodness. I don't know which is worse, this or the drawing. Actually, no, the drawing is definitely worse. So 15 minus 3 times 3.7995. We get an approximation of 4.15965 after half a second. Let's go and take a look and make sure that that makes sense. Take a look at our solution curve. So we were trying to approximate half a second, so that's roughly over here. If we go up, I didn't draw it perfectly, so it looks like it's around 4. Maybe I got skewed a little bit. Probably should have drawn this going up a little bit higher, but yeah, it's about 4.16, we could say. So in conclusion, how about we write that I of 0.5 is approximately 4.16 amps.